You know how we sometimes talk about space as this, like, vast unknown frontier?
Uh-huh.
Well, it feels like quantum physics has its own version. People call it a quantum zoo, just teeming with all sorts of bizarre and wonderful possibilities.
That's a great way to put it. And it's not just theoretical anymore.
Exactly. Just recently, researchers at Columbia University, they've announced some really remarkable discoveries, finding whole new species in this subatomic zoo, so to speak.
Yeah, that's right. And what's really exciting here isn't just, the number of new quantum states they spotted, but what these findings could actually mean.
Especially for quantum computing, right?
Precisely.
Yeah.
This isn't just about adding to the catalog of quantum weirdness, though that's cool too. It's about potentially finding states with properties that could, well, change the game.
Right. So today on the deep dive, we're jumping into this really groundbreaking research. It was published in Nature back on April 3rd, 2025.
The paper's called Hidden States and Dynamics of Fractional Fillings in Twisted MoTe₂ Bilayers. Bit of a mouthful.
Huh? Yeah, just a bit. But our mission here for you is to unpack how these scientists use this really clever optical technique, pump probe spectroscopy we'll get into, to find more than a dozen quantum states nobody had seen before.
And they found them in this specific material, twisted molybdenum ditelluride.
Which we will explain, don't worry. The main idea, though, is that they looked at this stuff in a completely new way and basically uncovered this whole hidden landscape of quantum potential.
Yeah, and to really get why this is such a big deal, let's talk a bit more about that quantum zoo idea.
Okay.
For years, physicists have theorized that when electrons interact in complex ways, especially at the quantum level, they could form all sorts of, well, exotic arrangements or states of matter.
Like theoretical creatures waiting to be found.
Exactly. Many were just math on paper predictions. This research gives us a real experimental window into that zoo.
And the sheer number they found is just, wow, over a dozen new states in one study.
It's pretty stunning. The lead author, Xiaoyang Zhu, even said, some of these states have never been seen before, and we didn't expect to see so many either.
You can almost hear the surprise in his voice, can't you?
Absolutely. They even made this visual map of what they found. You see these different peaks on a graph. Each peak basically represents a different state, characterized by a different fractional charge. It really gives you a visual sense of the sheer diversity they managed to uncover.
So, okay, fractional charges, quantum zoo. What's got people really buzzing, I think, is the link to topological quantum computing.
Ah, yes. The Holy Grail, some might say.
Right. It's this type of quantum computing that promises to be way more stable, less prone to errors than what we have now. What's the key idea there?
Well, the big hope for topological quantum computing is its inherent fault tolerance. See, current quantum computers, qubits, are incredibly fragile. The slightest noise from the environment can mess up the calculation.
The coherence, right?
Exactly. Topological qubits aim to encode quantum information differently, using the collective properties of these exotic electron states, which makes the information naturally protected from small disturbances.
Okay, sounds great. But there's been a catch, hasn't there? Usually involving magnets.
Yes, historically, the big hurdle was needing really strong external magnetic fields to coax these topological states into existence. But magnets, well, they can cause their own headaches, like interference, and they're bulky and hard to control precisely at that scale.
Right, so using magnets works in the lab maybe, but it's not ideal for building a practical computer, and this is where the new research comes in.
This is the potential breakthrough. They found these topological states popping up in this twisted molybdenum ditelluride without needing any external magnets.
That sounds like a really big deal.
It absolutely is. And the magic, it seems, lies in the material itself. This twisted molybdenum ditelluride.
MoTe2 for short.
MoTe₂, yes. It belongs to this fascinating class of materials called moire materials.
More like the visual pattern.
Exactly like that pattern. Imagine you take these incredibly thin sheets of atoms, just one layer thick, like graphene, but with molybdenum and tellurium. Then you stack two layers, but you twist one slightly relative to the other.
Just a tiny twist.
A very precise, small twist. That creates this larger repeating pattern, the moire superlattice, like overlapping two fine meshes. And this geometric pattern dramatically changes the electronic properties.
So the twist is basically everything here.
It really is key. Twisting these layers of MoTe₂ forces the electrons inside to behave differently. It actually makes the material intrinsically topological,
Mean.
meaning the electrons arrange themselves in ways that support these collective states, including those fractional quantum Hall charges we mentioned. But here's the really neat part. The twist itself, the moire pattern, effectively generates its own internal magnetic field within the material.
Whoa, really? So it doesn't need an external one because it makes its own?
Precisely. This internal, or effective magnetic field, is strong enough to enable these topological states, including the fractional ones, to emerge naturally. No big external magnet required.
That's incredibly elegant. The material provides its own special conditions.
It is. It's a beautiful example of emergent phenomena in condensed matter physics.
Okay, you mentioned the Hall effect and fractional charges. Can we break that down a bit? How does the regular Hall effect connect to this quantum version?
Sure. The classical Hall effect is something discovered way back. You run an electric current through a metal strip, put it in a magnetic field perpendicular to the current.
Okay.
The magnetic field pushes the moving electrons over to one side of the strip. This buildup of charge creates a voltage difference across the strip, the Hall voltage. Pretty standard electromagnetism.
Got it. More field, more push, more voltage.
Roughly, yeah. But then things get weird when you go quantum. You need extremely low temperatures, near absolute zero, and you can find the electrons to move in only 2 dimensions, like in these atomic layers.
Okay, extreme conditions.
Under those conditions, when you measure that Hall voltage, as you change the magnetic field, it doesn't increase smoothly anymore. It jumps in distinct quantized steps.
Plateaus, right? Like steps on a staircase.
Exactly. And the height of these steps is related to fundamental constants and the charge of a single electron. That's the integer quantum Hall effect.
Okay, integer steps. But this research is about fractional steps.
And that's where it gets even stranger. Under even more extreme conditions, stronger fields, colder temperatures, very pure samples, sometimes those steps themselves break down. You find plateaus corresponding to fractions of an electron's charge, like 1/3, 2/3, 1/2.
Fractions of an electron's charge. But electrons aren't supposed to split, are they?
They don't. That's what's so mind-bending. It's not that individual electrons are splitting. It's that the electrons acting together in this strongly interacting quantum soup create collective excitations, quasi-particles, that behave as if they carry a fraction of the electron charge. It's a profound discovery. Columbia's own Professor Emeritus Horststormer won the Nobel Prize for this back in '98, along with Sui and Laughlin. He said it implies many electrons, acting in concert, can create new particles having a charge smaller than the charge of any individual electron. It fundamentally changes how we think about electron behavior in these systems.
It really is like that orchestra analogy. The group creates something none of the individuals can do alone. So this fractional effect is key, and doing it without magnets was the next big challenge.
Yes, and there was a major step towards that just last year in 2023.
Ah, right. You mentioned precursor work.
Yeah, work led by Xiaodong Su, who's at the University of Washington, but also linked with Columbia's Research Center. He and his students, Jiaqi Cai and Hyunjung Park, published a paper, also in Nature, showing the first clear observation of a fractional quantum Hall effect specifically, a quantum anomalous Hall effect, meaning no external magnet in twisted MoTe2.
Okay, so they showed it was possible.
They did. They found 2 specific fractional states, proving the principle that this material could host these exotic states intrinsically. That really paved the way.
So Yu's team showed the door was open. How did this latest Columbia team manage to swing it wide open and find, like, a whole crowd of new states behind it? You said it involved some luck.
Well, maybe fortunate timing and the right tools.
Yeah.
Yiping Wang, who's a postdoc at Columbia, got a sample of this twisted MoTe2 from Zhu's lab.
Okay.
And while Professor Zhu, the lead author, was apparently away, Wang decided to try probing it with this technique called pump probe spectroscopy.
Pump probe. Tell us how that works.
It's pretty clever. Think of it in 2 steps. First, you hit the material with a quick, energetic pulse of laser light the pump. This basically injects energy, sort of melts or disrupts the delicate quantum state the material is in.
Okay, you shake things up.
Exactly. Then very shortly after, you hit it with a second, weaker laser, pulse the probe. This probe pulse measures how the material's optical properties, like its dielectric constant, change as it recovers from the pump pulse.
And that tells you about the quantum states.
Yes, because as the system settles back down, different quantum states reemerge, and each state affects the light absorption or reflection slightly differently. This probe pulse is incredibly sensitive to those subtle changes.
And this specific pump probe setup they used was key.
It seems so. The method, which was refined by another team member, Eric Arsenal, is apparently extremely fast and sensitive. It allowed them to resolve the tiny energy signatures associated with all these different fractional charge states that were potentially forming and dissolving.
So sensitive it could pick out things others missed.
That's the idea. Professor Zhu actually stated that this discovery really establishes pump probe spectroscopy as potentially the most sensitive technique we have right now for detecting these kinds of quantum states.
And the results just blew them away, finding dozens of these fractional charges.
Absolutely. Not just the two Zhu found, but a whole spectrum of them. And crucially, some of the fractional charges they detected correspond to states that theorists have been predicting are needed for topological quantum computing.
Like the non-abelian anyons you mentioned, that sounds incredibly exotic.
It really is. Non-abelian anyons are theoretical quasi-particles with very strange properties.
Yeah.
If you swap two identical ones, the overall quantum state of the system doesn't just get a phase factor like normal particles, bosons or fermions. It can actually change into a different state within a whole set of possibilities.
Okay, that's weird. How does that help with computing?
That memory of how they were swapped or braided around each other could be used to perform quantum logic gates. And because this braiding is a topological property, it's expected to be very robust against local errors. Finding evidence for these in a real material, especially one without external magnets, is incredibly exciting.
Wow. So it's not just finding new states, but finding states that might actually be the building blocks for this fault-tolerant quantum future.
That's the hope, yes. A very significant step in that direction.
And this technique, the pump probe, it doesn't just see what states are there, but also how they behave over time.
That's another powerful aspect. Because you're hitting it with a pump and watching it recover with the probe, you're inherently studying dynamics. You see how these states form, how long they last, how they might transform into one another.
So it adds a time dimension.
Exactly. As Yeping Wang put it, it feels like we've entered new dimension, time, to explore correlation and topology. They just keep surprising us, especially when we push them out of equilibrium. It opens up a whole new way to study how these complex electron interactions and topological properties unfold.
That sounds fascinating. So they found this treasure trove. What happens now? What are the next steps for the researchers?
Well, the immediate task is to really characterize all these new states they've seen. There are over a dozen, remember?
Right.
They need to figure out the precise nature of each one. Are they abelian? Are they the non-abelian ones? What are their specific properties? And then crucially, which ones are the most promising candidates for actually building qubits?
So sorting through the zoo to find the potential superstars.
You could say that, yeah. Professor Zhu basically said, there are just so many. We hope these results in our technique inspire others to explore. It's really an invitation to the wider physics community to dive into this rich new landscape.
It really does feel like a pivotal moment, doesn't it? Like opening a door to a room full of things we didn't even know existed.
It definitely has that feeling. This work dramatically expands our map of possible quantum states, and it points towards a practical route, magnet-free, for harnessing some of the most exotic ones for topological quantum computation. It's a double win, really.
A huge step for fundamental physics and potentially for future technology.
Absolutely.
Yeah.
It tackles a major bottleneck in topological quantum computing while simultaneously revealing just how much complexity and richness lies hidden in the interactions of electrons in these carefully engineered materials.
So, wrapping up this deep dive into the quantum zoo, it really leaves you wondering, doesn't it? If this new way of looking revealed such an unexpected diversity of quantum states, what else is lurking out there? What other bizarre quantum species might we discover as our experimental tools get even more sensitive, more clever?
It's a fantastic question. We're peeling back layers and finding more complexity than we perhaps anticipated.
And what kind of fundamental shifts in how we understand the universe could these future discoveries lead to? It's genuinely an exhilarating time to be watching the exploration of the quantum world.